How you doing? I'm Mr. Rose, and you caught me in between some light reading. Again, we're using your University Physics textbook, 13th edition, Young and Freeman, and we're in Chapter 22, Gauss's Law. And right now we're going to tackle question 53, but only Part A. Part B is going to be left for you. And again, read the question. As always, I encourage you to try what we're doing before you watch me go through. The reason why I have it written out this time is because last time that was kind of an epic failure. So this is a sphere, and it's an insulating sphere I have written, and they gave us a charge density of alpha divided by A, where alpha was some positive constant. Now part A is asking us to find the magnitude of the electric field, and they're asking us to do that in between surface A and surface B that I have here, my cross section of the sphere. So you can see I have radius A, I have radius B, and then I have this radius R, and that's really what we're looking for. We're looking between A and R. So to try and find the electric field, this is one of my favorite type of problems. This is one of those indirect type questions. If I get my head in there, there we go. So I know Gauss's law. The antiderivative of E dot dA, and that's my surface integral, is equal to Q enclosed over epsilon 0. So the only thing I'm given here is this charge density, and charge density has that key word, charge. So we're going to need to use that charge density to find out what our Q is. And as we know with Gauss's law, if I know a charge, I can find an electric field. If I know an electric field, I can find a charge, etc., and so on. So I'm going to come back to Gauss's law later, but we're trying to find this Q enclosed. And Q enclosed is really some Q at some radius R away, right? Because again, I'm looking in between A and B. So I'm looking at any radius in between my black line and my purple line there. So, excuse me. I know I know Q, this is my Q enclosed, Q of R, and I'm going to integrate because I want all of those possibilities. So I'm taking the antiderivative from R1 to R2 of my charge density, again, that's charge per unit volume, dr. Well, how am I going to get that to be useful? Well, I know rho is alpha over r. That was my given information. And to make my charge densities work, I'm taking that surface area, that 4 pi r squared. So now here I have the antiderivative of my rho, alpha over r, 4 pi r squared, dr, at any value dr. That's what I'm integrating across. I pull out my constants. As you can see, this is kind of self-explanatory. After this trick is really the physics. I pull out my constants. Now I'm just integrating from R1 to R2 of R dr, and I got a general solution of 4 pi alpha r squared over 2 from R1 to R2. But remember what I'm looking at. I'm specifically looking between A and B. So really, R1, I just rewrote out here, R1 is just my A, and R2 is any value R that's less than B. So I can't go from A to B. It has to be from A to R. That's kind of important with my limits of integration. When I sub that in, I now understand that my Q enclosed is given 4 pi alpha times R squared over 2 minus A squared over 2. Now that I have my charge, I can apply Gauss's law. So I've rewritten my enclosed charge here, 4 pi alpha times 1/2 r squared minus a squared. Now I know what you're thinking. You're thinking, should I cancel that 4 and that 1/2? Well, I didn't specifically for a reason, and you'll see that as we go. So now I'm applying Gauss's law. E dot dA is my Q enclosed over epsilon 0. And when I take the surface integral of E dot dA, it's just E times A. And I have a little asterisk there that I'm going to come back to in a moment. Is equal to, now it's just a direct substitution. Q, there's my Q over epsilon 0. Now this E is not my electric field everywhere that I'm solving right now. Again, I'm solving for my electric field. Let me just bring this picture back up. I'm solving for the electric field somewhere between A and B at some radius R. So I've subscripted that as my electric field at some radius R, meaning I am looking specifically between surface A and B. So now I have ER is equal to my area, 4 pi r squared. Again, that's my surface area. I think I misspoke before I said volume. My surface area, 4 pi r squared of my sphere, is equal to just my charge enclosed. And remember I said, should we cancel that? We shouldn't, because 4 pi r squared, 4 pi, I can cancel that right out. And now I'm left with, when I simplify, E of r is equal to my constant alpha over 2 epsilon r squared times r squared minus a squared. I notice my r squareds here, excuse me, so I can simplify and get something in a simpler fashion, or simplest form. My electric field at any r in between those surfaces of my insulating spheres A and B is just alpha over 2 epsilon 0 times 1 minus a squared over r squared. Again, I'm leaving B for you to try. That's all I have for this example. Again, that came from Young and Freeman, chapter 22. This was question 53, I believe. I don't remember because I closed the book. If this is on YouTube and you're watching it, please feel free to like, click, comment, or subscribe. And that's it. You'll see me next time.